Hi, my name is Dr. DrAlanBarnard. I'm CEO of Golden Research Labs. It's a great honor to do this presentation today. The title of my presentation is Simulation Modeling of Complex Project Portfolios. There'll be three parts to the presentation, starting off with what is the challenge that we are facing. Secondly, what could be a direction of a solution, and then to present three case studies, one for simple projects, one for complex projects, but high volume, relatively simple project networks. And then the third type of category, complex projects, low volume, but high complexity in terms of number of tasks and dependencies. And each of those, I'll be presenting a simulation model of that environment to show the type of insights that we can gain through simulation modeling. I do have a second session for the day after, on day 2 of this conference, where I will be actually taking you through these simulation models and open it up for questions and answers with attendees. So let's start. So what is the challenge that we're facing? Well, in any and all complex real-life systems with uncertainty, there are major challenges when it comes to decision making. First of all, it's really easy to make decision mistakes in these environments. And secondly, it's extremely hard to learn from the decision mistakes when we do make them. Why is that? Well, it's easy to make decision mistakes simply because there are always many more ways to fail than to succeed. If you think about a simple recipe, you have 4 ingredients, you have 4 steps, you have 1 temperature setting. How many ways are there to get it wrong? Well, many ways. How many ways are there to get it right? Very few ways. The same is true for projects. We have the same type of thing. We have a number of steps that we have to go through, a number of phases that we have to go through in order to deliver a project. There are dependencies between those. And of course, we have resources that we have to deploy, and those resources have to be available. Many of those things can cause failure. And as a result, it's pretty easy to find something to blame when we don't succeed, when we deliver late, when we deliver at a higher cost than what we expected, or if we don't deliver the full scope. Secondly, is that it's easy to make decision mistakes simply because the type of rules that we are using for planning the work in a project environment, the rules we are using to make decisions around the execution of that work and the measurement and improvement of that work, often the rules that we need for global rather than local optimization can be quite counterintuitive. And as a result, it's pretty easy to make mistakes from a local perspective. Multitasking, which is one of the examples I'll show, is like that. From a local perspective, it's extremely counterintuitive to not multitask. And lastly, why it's so easy to make decision mistakes is that often small changes that we might think are not consequential, can have big impacts, either positive or negative. Why is it so hard to learn from our decision mistakes? Well, firstly, in real life environments, typically large time and often space gaps between causes and effects. We are programmed and have the biology to learn very quickly from mistakes. Touching a hot stove plate, we can learn hopefully after the first such event, because it's easy to learn because of that short gap between the cause and the effect. I want you to think about a situation where, imagine if you got burned just a day later. How long will it take you to put those 2 events together to see the correlation? And if it's a week later or a month later, and that's often what we see in complex environments like projects where there's a large time gap between something that happened, either an internal or external change, and when we see the effect. And being able to go backwards, it's really hard. Secondly, as with the making decision mistakes in planning, execution, and in improvement, to learn from those mistakes, if the changes that we made was counterintuitive, or the changes that we need to make was counterintuitive, it's often very hard to put that. So if your project is late, before we knew how bad multitasking was, would you ever go back and look for cases where people were multitasking to come up with an explanation of why you didn't achieve the targets that you had set out? And lastly, as I mentioned, small changes can have big impacts. A practical example of this would be, imagine a company with 100 in sales and 5 in net profit. That could be $100,000, it could be 100 million, doesn't matter. A 1% increase in the average selling price of the products or the services or the projects that this company delivers. Variable costs won't go up, your operating expenses won't go up, so that whole value addition will drop to your bottom line. So your sales would go from 100 to 101. That one will drop to the bottom line. Your profit will go from 5 to 6. That's a 20% increase in net profit. Now imagine you get to your management meeting and you're trying to explain why your profits for the last month has gone up or down by 20%. How many people would think that we should check whether the average selling price of what we are selling didn't go up by 1%? And it's that element where small changes can have big positive or negative effects that make it really hard to learn from experience. So if this is the challenge, it's easy to make decision mistakes in complex environments. It's very hard to learn from them. When we do, is there a solution? And the solution that I'm presenting today is building digital twins, dynamic simulation models of these real life systems. Over the past, especially the past decade and maybe even 5 years, there has been massive advances in building digital twins that help us to overcome these limitations in a very practical way. And our goal with digital twins are very simple. We want to give access to decision makers to this technology so that it's harder to make decision mistakes, because we'll be able to predict much more accurately what the impact of our decisions will be. And secondly, that even if we do make a decision mistake, it'll be much easier to learn from our decision mistakes, because in a virtual environment, we can literally press the rewind button, go backwards in time and isolate what are those events that could have caused the effect that we are currently seeing in our environment. Before I get to the simulations, I'd like to share with you a framework that I've developed that can explain the types of decisions that could have an impact on the goals that we are trying to achieve. And I've separated these into planning decisions, execution, and improvement decisions. So let's look at what is the goal that we're trying to achieve. Is that we want to achieve more faster with lower cost. In a project environment, that would be achieving more projects, getting our throughput to go up faster, which means reducing the total flow time. That's both the time it's spending in backlog potentially, as well as in queue and in process. And at the same time to do that with lower cost. We obviously, the objective is that we do that to fully meet the demand that the system is placing on us. How are we going to do that? We know that in order to achieve more faster with lower cost, we have to continuously improve and synchronize the flow of work. And by continuously improving flow, we specifically mean reducing flow time in order to get flow rates up. Now, how do we go about doing that? There's essentially 3 leverage points in the system. There's planning decisions we make before we start the work, execution decisions, which is decisions we make while we do the work, and improvement decisions, which is decisions we made after we've completed the work. We can reflect back, we've got some measurements, and now we can decide what to change and what not. For each of these, there are essentially 2 categories of decisions. So in planning, the first of those categories has to do with decisions we make before we start doing the work that will involve how we allocate our resources, and specifically also our buffers. How do we buffer in order to reliably meet demand at the lowest cost? And how we buffer means not just the size of the buffers, but where do we place those buffers and what buffering mechanism are we going to be using? The second major decision is, once we've decided on the allocation of resources and how we're going to buffer, We have to make reliable commitments. We have to be able to quote reliable lead times, for example, but we also have to control and synchronize based on those commitments how we are releasing WIP into the system. I mentioned that there's a backlog component, which is before we release it. And then once we release it, it goes into process and into queue. We need a way of controlling and synchronizing the release of work. That's on the planning side. On the execution side, the first major category of decision and execution is how are we actually going to do the work? Are we going to change the priority based on some local consideration or some global consideration of the work that's arriving? So we might decide to either process it in the sequence that it's arrived, or we might decide to change the sequence of arrival. How do we make that decision? And secondly, also, are we going to be batching or multitasking, or literally taking it one at a time? And then the second type of decision we're making in execution, which is a decision while we're doing the work. We are now working on the decision. We might notice that there's some problem, there's some delay. When should we expedite, and what should we be reporting? That's the second category of decision and execution. And then on the improvement side, we essentially have two categories of decisions on improvements. As what should we be measuring that will tell us how the system is doing as a whole, and what the causes of the performance is, rather than just measuring locally. And lastly, based on those measurements, when and where should we make improvements or adjustments, and when and where should we make investments? Now, in the framework, I'm sharing with you in this framework also what are the conceptual mistakes that can be made in each of these major decisions, and what is the principle that can be used in order to reduce or even prevent that mistake. Now, the purpose of this talk is not to take you through each of these, but I'll highlight some of them as I go along. I've included this slide in the slide deck for you to review, and you're welcome to send me questions if you might have questions. So let's go through the case studies. The first case study I want to present is a very simple project environment. It's one that probably many of you have considered when you are training people on concepts like critical chain project management or agile. And it's a project environment where you really have only 3 projects to do. Each of these projects are made up of a few tasks, and you have to decide how are you going to make a commitment. When will you have not just all 3 projects completed, but each of the individual projects completed? That's your first big decision. How do you make a commitment in such an environment about when you will be able to complete these projects? And secondly, how do you execute these projects? Now, these decisions are made together because your mode of execution can impact quite dramatically, not just the commitments that you've made, but also the confidence that you might have in meeting those commitments. So we created a multitasking simulator. This is similar to the game that many of us have played. I developed one of the versions of this game back in 2006 when I started doing my PhD. And the game works in a very simple way. It basically shows that you've got 3 simple projects to complete. In our simulation, you can decide whether each of these projects have got 5 tasks per project, 10 or 20 tasks. These projects involved essentially writing characters on a page. The first project is writing down numbers, 1 to 5, 1 to 10, or 1 to 20. The second project involves writing down letters, the first 5, 10, or 20 letters of the alphabet. And then the third project involves writing down symbols, which could be just 20 symbols that you might repeat. When you're writing one of these characters, you'll notice that the time per task is about ½ a second. Now, how do I turn that estimate of the actual time it will take me to complete the work into something that I might be willing to make a commitment on? And we'll apply a very sophisticated buffering mechanism, which is essentially take that time estimate and multiply it by 2. As a result, we're going to be assuming that with a bit of a buffer, each of these tasks should take us no longer than 1 second. If we've selected the option with 10 tasks per project, 10 tasks, 1 second per task, free project, that means our total commitment is going to be 30 seconds. Now, if we were multitasking, so essentially switching from project to project, writing the 1, then writing the A, then writing the first symbol, then switching back to the numbers project, writing the 2, then the B, etc. You will see from the Gantt chart that we've got there that probably you'll be making a commitment of around 30 seconds for all 3 projects. And you could theoretically commit to 28, 29, 30 seconds, but practically we'll say about 30 seconds for all 3 projects. That's a very different commitment that you'll make, that we'll see now when we go into single tasking mode. In single tasking mode, I'm going to do the first numbers project. I'll commit to 10 seconds for that. Then do the next project, which I'll commit to also 10 seconds, but it will complete at time 20. And then the last project, also a 10-second project, the symbols, but that would complete it at time 30. And that makes quite a dramatic difference in the way that we are making commitments. So let's see what the execution looks like. In our simulation, you can choose to either simulate it or you can play it manually, almost like you were writing it down. The simulation mode is using actual times from hundreds of such cases that we've had in the past of people playing the simulation game. So we can provide an accurate estimate of what a real life scenario might look like. So how it works is in the simulation, you see the projects and tasks in the center there. And what you'll notice is that the tasks are then color coded. And when it becomes green, it means that you have to now complete that task. You will move your mouse over to the numbers pad there and click on the 1. Then the A will light up. You will go take your mouse down to A. You will click on that button and then you'll go to the symbols. Maybe the square will light up and you'll do that. Essentially, the way that we are executing the project is we're going zigzag. We are switching from project to project, not just from task to task. And as you'll see from the actual performance compared to the planned performance, in this case, the actual performance was around 10 seconds longer. So about a third of the time longer than what we expected, finishing it in just over 40 seconds. Now, could we do better if we were single tasking? Not just for the overall portfolio, but for the individual projects. You'll notice here that all 3 projects ended up finishing at about 40 seconds compared to our commitment of 30 seconds. And this is what happens in a single tasking environment. We are actually finishing the projects faster than what was planned, simply because we realized we didn't need so much buffer. And an interesting part is obviously the way that we are doing these projects is we're minimizing the switching of projects. We can't help, we have to switch tasks, but we don't have to switch projects so often, which is often the biggest cause of the delay. And yet here we can see we finished it in around 23 seconds, or about 7 seconds sooner than what we expected. When we compare the performance in terms of the Gantt charts, it's very obvious that from a planning and execution side, we are doing much, much better in the single tasking mode. But then what the simulation allows us to do is literally go back in time and monitor exactly where did we lose the time. Now, in a multitasking environment, what we've picked up is on average, when people are pushing themselves to try and finish it as quickly as possible, they tend to make about 3 mistakes in the 30 tasks that they're completing. So they might be clicking on the wrong button or clicking on the right button in the wrong sequence, etc. So that's about 3 defects. They are constantly having 3 projects in progress. And the total time that we showed was 40 seconds. Now, how is that made up of? The actual time to do the work, which is clicking on the right buttons, took about 18 seconds. Switching from task to task was about 7 seconds. And by far the biggest loss was switching between projects. And that took an additional 14 seconds. Now that is really useful because it shows us where are we losing time and what solution would save us the most time and therefore increase our performance. How much improvement can we expect? We can also quantify the difference. The duration was 42% longer in the multitasking than in the single tasking. So if we can essentially remove the avoidable causes, we should expect a reduction in our lead time of around 40%. How did we do that? We reduced WIP by 2/3. We went from 3 to 1. That impacted also the quality side. We essentially completely eliminated the defects, and we at the same time increased our throughput by 74%, going from 0.74 tasks per minute or per second to 1.29 tasks per second. So that's the first case study that I wanted to share with you. It's a simple project environment. Let's look at the second one, which is a more complex project portfolio. But in this case, it's complex not because of the nature of the projects, but rather because of the high volume of the projects. So a way of simulating this environment is by simulating traffic flow. So imagine a project is essentially a car arriving. When it arrives, it goes into backlog. It cannot get onto the freeway immediately. There's some level of control that happens to allow it to get onto the freeway, which is representing our project system, essentially. Once it goes onto the freeway, it will complete 2 rounds here, which represents the actual work that needs to be done on it. The driving time, if there were no other cars on the road, would represent a theoretical work time like we saw in the previous example. And in the cases where it's waiting for the resource to become available, which is the road, and also it's being slowed down by other traffic, that's representing all the potential avoidable delays. So let's look at 4 scenarios here. The first scenario, we're going to just allow the traffic to enter. This is a time period between 6 o'clock and 10 o'clock in the morning. And what you'll notice in the blue graph there is very quickly a backlog of cars built up, not just on the road itself, but waiting to enter this road system, our project system in this case. And as a result of the backlog, we have a dramatic reduction in the ability to achieve our goal, which is to arrive within the planned time at our destination. On the right-hand side in the top there, the quoted lead time as we show how we do the calculation. So the best case scenario, if a car can immediately get onto the road, there's no other cars that can then get off and arrive at its destination, is around 5 minutes. A typical time on the circuit, considering other traffic, is around 20 minutes. And a typical time in backlog over this time period is around 40 minutes. And that's why we made a commitment of 60 minutes to complete the work. And that's also true in a project environment. We normally have these 2 elements. We have what time do we expect a typical project to stay in backlog before we release it to start working on it, and how long typically does it stay in process. And the extreme of the in-process time on the left-hand side, what's the minimum time, is essentially just the sum of all the work time that's required. All the rest is essentially our allowance for in-process delays, where it's waiting in queues, waiting for a resource or waiting for other tasks to complete. So you can see that the performance is pretty terrible. Our on-time performance was really shocking. A lot of black, essentially the cars that arrived late or the simple projects that arrived late. What we did in scenario 2 is we said, what if we take exactly the same arrival rate, so same demand pattern, but in this case, we just apply a very simple rule, which is controlling the WIP. We don't allow more than, in our case, about 175 cars on the road. So that's a WIP control mechanism. There's no prioritization based on buffer status or anything else, just purely controlling the WIP. And you can see from the graph, it already looks much better. We have a much higher level of adherence to plan. Essentially, on-time performance has gone up dramatically, but also the time to actually execute have gone down dramatically. And you'll notice on this curve here in the we don't get that exponential growth. So in this case, there was no traffic jam that built up, whereas in the previous case, you can see how that lead time grows exponentially as we hit that demand peak. In the second scenario with the whip cap, we never reached that. And we maintain a pretty good level of throughput right throughout. In the next scenario, what we are doing is not only applying that whip cap, but also what we are doing is we are color coding the work when it arrives. And during the backlog allowance time period, we make it blue. As soon as it gets onto the circuit, then it goes through the simple phases of green, yellow, red. So if we've got a 40-minute backlog allowance, that will stay the blue. So for the first 40 minutes of that 60 minutes, it will remain blue. Then it gets into the time that we've released it now, that remaining 20 minutes, and the first third of that will be green, then yellow, then red, and then if it's over time, black. And you'll notice from the performance adherence, they're much less black than in the previous round, and very good performance in terms of duration as well. We're actually completing work on average faster than what we expected. In the last scenario, what we're doing is essentially three things now. We are applying a whip cap. We are applying the priorities based on the colors, but we're also using some of the capacity that we've got to only work on the reds and blacks, so they also get priority assistance. And we have a smarter way than just a very simple static whip cap to release work into the system. As you can imagine, like in real life cases, the demand over time goes up and down. And as a result, we really shouldn't be using a static whip cap. We should be using a more dynamic whip cap, which is, in this case, we called it smart whip release. And you can see the performance is massively better. We never get close to any traffic jams, and we get to 100% on-time performance. So just as a direct comparison of these four scenarios is in our baseline scenario, we committed to around 56 odd minutes, and we actually delivered most of the time in 72 minutes. So there was a 16-minute on average delay, but our on-time performance was only 48%. When we introduced the whip cap, on average, we were actually completing work faster than what we expected, taking only 49 minutes compared to a planned number of 56 minutes, so 7 minutes faster. But we also got our on-time performance a little bit higher. We got it up to 58%. So we're doing it faster and even more reliably. As soon as we introduce not just a whip cap, but also priority lane. So when work goes into red and black, we are not just putting them ahead of the other work, but we're giving them special attention. In this case, we are allowing them to use a lane that's normally occupied by vehicles that are carrying 2 passengers. So we give it a special pass that says you can use that because you've got it into the red or the black. We don't want you to be late. And again, using the same capacity, exactly the same capacity, same demand profile, we're now doing it 13 minutes faster. And then the last portion is where we are using the smart traffic light to not just use a static whip control, but to do it in a more smart way, where we are dynamically changing our whip limit based on the demand profile and available capacity on the road. And as a result, we get a much, much better performance. We're now achieving 100% on-time performance, and on average, the work is completed in 14 minutes compared to that baseline scenario of 72 minutes. A very, very dramatic improvement. This is also true for any project environment. You can use exactly the same type of rules, introducing the whip cap to get it under control, introducing the next change as a prioritization to decide what sequence should be processed and who to give special attention to. And then the last part, the more advanced part of the solution, is to developing a simple mechanism that can provide a dynamic way of controlling the whip, not just a static way of always keeping the whip limit at exactly the same. So then the last scenario that I quickly want to go through is a more complex scenario. And in this case, it's complex because of the nature of the project. So it's relatively low volume, unlike the second case study that I presented. And in this case, I'm presenting to you our project portfolio management simulator. And The types of projects is going to be construction projects. So this company is a company based here in the US, and they are building condos, and they have a large portfolio of condos that they have to deliver for different developers. And when we looked at a typical project, it's made up of 4 phases of the design part, the building the foundation, that involves the excavation, the pouring the foundation concrete, and then leveling it off, the actual construction part, putting up the walling, the windows and doors, then the roof, and then finally finishing, painting and tiling, the interior side, landscaping, and then final inspection. A typical project like this, the revenue from a condo is about 1.3 million, and the expected profit is about 20%. And what we want to do is to see, they've given us their portfolio that includes 12 of these condos, 6 of them in the Los Angeles area, 6 of them in Las Vegas area. They've given us all the resources. We want to simulate to see what's actually going to happen. And their planned start date was the 2nd of December. Their planned completion date was the 16th of March of this year. So slightly over a year of work. And what we can do in the simulation is we can model different scenarios. So we can model perfect world, which is essentially simulating what if they didn't implement any best practices from critical chain project management or agile. They literally just executed the work as they were planning. And of course, you can imagine all the work was starting as soon as possible, which would probably trigger some multitasking, some starting things without the full kit, etc. We want to model what that would look like in a perfect world, which is there's no demand volatility or lead time volatility, versus a real world where there could be changes in the actual time it takes to execute the tasks. And then we modeled different scenarios. Round 2 was applying a WIP control mechanism, but controlling the WIP at the project level, which essentially is, in this case, those major phases that they're going through. Or we can control it at the program level, which is the release of when they're starting a new condo, or a kind of a hybrid environment where we are controlling the release at the program level. But if we see some of the critical capacity constraint resources running out of work, we can override that WIP control mechanism and release additional projects to keep those critical resources busy. So when you click on the play buttons, essentially it will bring up the performance. And as you can see from the fever charts on round 1, which is the baseline environment, many of the projects were actually completed late. In rounds 2, 3, and 4, many of the projects suddenly completed on time. There were still a few that were late, but let's look at the on-time performance. So in the real world environment here, compared to the perfect world, in a perfect world, they would have been only 3 days late. So if there were no variability in the task durations, their plan was pretty solid. They would have been around on time about 3 days late over that. But as soon as you introduce task variability in terms of the time it takes to execute the task, they would have been 44 days late on that commitment that they've made. In round 2, where we're controlling WIP at the project level, they would have been 50 days earlier than the 44 days late, which means that they would have actually completed all the work earlier than what they've committed to. A very interesting one was controlling the WIP at a program level is not a great idea. In this environment, it might be the best idea in different types of environment, but in this type of environment, controlling the WIP at a program level was not a good idea. It only saved us about 5 days compared to the baseline scenario. And then by far the best scenario in terms of time, at least, was the hybrid environment where we're using a combination of WIP control, both at the program and project level, essentially maintaining the flow of work at that sort of good enough level, the sort of inverse U shape, not to have too much work, not to have too little, and dynamically modifying that based on monitoring what is happening with our scarcest resources. In that case, we could have finished all the work 70 days earlier. We're also modeling not just operational performance, but our financial performance in our simulation model. And very interesting, our plan per condo was about 1.3 million in revenues. Total cost about $1 million, so a gross profit or net profit of $300,000. In the baseline scenario, they essentially would have lost $30,000 on every condo, or $300,000 on every condo. So a massive swing about just because of those delays that would have caused your cost to go up without revenues going up. In round 2 scenario, we got to $1 million profit, which is incredible. And it basically just shows you, in this case, the company has got quite large fixed costs. So if you can do more projects in less time with the same fixed cost, your net profit will grow dramatically. The other reason for the net profit to grow is that they've actually negotiated bonuses for early completions. And you can see a big chunk of that net profit are those bonuses, because as soon as they can deliver, the developer can start getting the rent of those. In the baseline scenario, they incurred some of the penalties for late delivery, which is one of the things that the developer required them to commit to. In round 2, profit was about $640,000. In round 4, the one that gave the best overall performance in terms of lead time was also close to $1 million. So it's a really interesting result that we got from this. And just as a summary of what are the final thoughts that I want to leave you with is, in complex environments like project systems, how do you know you can do better or even much better? Second question is, how do you find a better way? Not the best way, but the better way of doing better. And I specifically say the better way of doing better because in real life environments, there's no optimum points. All that we're looking for is simple rules that we can implement either in planning, execution, or improvement that will improve our performance, make us do better or even much better. And then the last question is, how can you test the hypothesis of number 1 or 2 in a low cost, low risk way? Well, regarding number 1, one way to check if you can do much better is to compare your best performance versus average, or best versus worst. So in a project environment, typically, if you've done the same type of project a few times, you can say, what was the fastest we've ever done this? How does that compare with the average versus the worst performance? Obviously, if you have a lot of data, you can go back and analyze the data and see, what if there were no delays? How does the actual work time compare to the total lead time? And in a project environment, that's normally at least 50% is just work time. The rest are all mainly avoidable delays. How can you find better ways to do it, to do much better? Well, there's 2 ways of doing it. The one is to think about what were the conditions that were in place that allows us to achieve the best to date. And typically what you'll find is the conditions were that we had a full kit when we started. We didn't multitask. We focused on doing one main phase at a time and getting it done. We didn't spread our resources too thin. We had a clear way of prioritizing and making everybody's priorities synchronized. So that's one way of discovering better ways, is to look at what conditions enabled you to achieve the best to date. But of course, we also have great best practices like critical chain project management and agile. And what we want to do is we want to identify what are the main causes of the flow delays, flow time delays, throughput losses, and avoidable expenses. Once we identify what those main causes are, we can then identify what are the new decision rules that we need to implement. So is it mainly a problem on the planning side? Is most of the delays happening because we make mistakes in planning? Or is it mistakes that we make in execution or in an improvement side? And by mistakes, it literally just means we're using some rule that causes some form of local or short-term optimization at the expense of global or long-term optimization. And then the last part that I hope I convinced you with is we can easily test today these type of hypotheses by building digital twin simulation models of our project management systems. In the past, it would have taken us months and sometimes years to build these models. Today, we have platforms that can build these models almost instantly directly from data that already is sitting in your IT systems. I hope that was useful. In the session that I will do tomorrow, I will actually show you live these simulation models and hopefully allow a lot more time at the end for answering any questions that you might have, either on the principles that I shared today or on one or all of the free case studies that I presented. Thank you very much for your attention.